Let's continue to look at question 1 about span, which is whether or not a given vector is in the span of a set of given vectors. And so this is the same problem that we looked at just a moment ago, except I've gone in and added a third vector here. So another one that looks much like the second one, except for being 1 minus 1, 1, it's 1 minus 1, 2. All right, and so now we'll ask the same question, is that same vector b in the span of these vectors? Okay, so now the question of whether or not we can write b as an element of the span looks the same as before, except now there's a sum of 3 things, right? And so when we translate this into a matrix equation, we have 4, 0, 2, 1 minus 1, 1, 1 minus 1, 2. And we're multiplying this against some vector of length 3 called c, with entries c1, c2, and c3. And this should be 2, 2, 1 if we have a solution for it, right? So now notice that the question is just whether or not a solution exists. We're not actually asked to find the solution. So in this particular case, since we have that this is a square matrix now, this is a, let me just clarify, this part is we have a square coefficient matrix. That unlocks the ability to use the determinant. And we know from the characterization of invertibility theorem that if the determinant is non-zero, then the matrix is invertible, and if the matrix is invertible, then there exists a unique solution. So let me say that again. If the determinant is non-zero, then the coefficient matrix is invertible. And one of the things that's equivalent to the coefficient matrix being invertible is that the system AX equals B always has a solution, and it is a unique solution. So I can check the determinant, and so doing some products here, let's see, so we have minus 8, and coming down this one here is going to give me minus 2, and coming down this one is going to give me 0, and going up the diagonals I'm going to have minus 2 and minus 4 and 0. So my determinant is going to be minus 8, minus 2, plus 2, plus 4, and that gives me minus 4. Definitely non-zero. Okay, so then that tells me that a solution exists. And that would be enough to solve this problem. Now, if you actually wanted to know what those coefficients C1, C2, and C3 are, if the problem was phrased slightly different, or maybe you were just curious, whatever, you could go ahead and find that by doing what we did last time, which was to row reduce the augmented matrix. And if you do that row reduction, you will get the identity here because the determinant of the coefficient matrix is non-zero, so it's invertible, so its reduced row echelon form of the coefficient matrix will be the identity. And you end up with 1 minus 3, 1 over here on the right side of the bar. And so that tells you then that v1 minus 3v2 plus v3 is equal to b. And checking that numerically, v1 is 402, and we subtract 3 times 1 minus 1, 1, and then we add 1 copy of v3, which is 1 minus 1, 2, and you will indeed end up with 1 minus 3, 1. I'll leave that to you to check the arithmetic on that. Let's look at one other example. So so far, all the vector spaces we've been talking about have been R3, but there are other vector spaces we've seen that. So I could ask you a question like, say, is the matrix 1, 2, 0, 2 in the span of 2, 0, 0, 4 and 1 minus 1, 0, 1 and 2 minus 1, 0, 1. Okay, so these are all upper triangular matrices. We've seen that the upper triangular matrices form a vector space, so it's fair enough to ask if this one that I've given you is in the span of those other ones there. So let's see. So that question would be answered by trying to determine whether or not there's a coefficient C1 such that if you did C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix, you would end up with the given matrix. All right, so can we solve this? Well, let's just look entry-wise. So, for example, this entry of the matrix right here is going to be C1 times 2 plus C2 times 1 plus C3 times 2. So that gives me an equation there in purple. We have 2C1 plus C2 plus 2C3 equals 1. And similarly, collecting the terms from the other entries in the matrix, we would get the equations minus C2 minus C3 equals 2, and 4C1 plus C2 plus C3 equals 2. And so now we've got this question about matrices converted back into a question about linear systems. And so now we can solve these in any of the usual ways. So for example, look to see if 2, 1, 2, 1, 0, minus 1, minus 1, 2, 4, 1, 1, 2, the augmented matrix, see about row reducing it. And by now you've probably already noticed that this is actually the same matrix that we had in the previous example. So you know this is going to row reduce to something that has the identity here. And that's going to be your recipe for how many of those matrices to add together to give you the matrix 1, 2, 0, 2. So if you go back to this example right here, this matrix was just formed by writing in the first, second, and third entry of the corresponding matrix vector V1 from the previous example, and that's how I set up this whole thing. The interesting offshoot about that is that these questions about matrices can be rephrased in terms of questions about vectors, basically just by rewriting things in a different position.